Yes, I will start the class. In the last class, I have explained about the validation metrics. In the case that the computer model is deterministic, but the experimental data includes the associated uncertainty. And under this condition, at first I started with the comparison of means between the two, the one from the model, the other from the experiments. And the first case was about the results at a single point. So the validation metric was made based on a single point, one from the model, the other from the experiment. Then I moved to the case including the multiple points over a range of input variables. And in that case, the textbook introduced two cases. One was the case of very many experimental data available over that range. And the other was a case of only a few data were available over the range. And within the case of a few data, he introduced the regression of approximation of the experimental data using either the linear or the nonlinear regression. Whatever it was, in the end, what we got was some kind of a validation matrix, and it represents the difference between the deterministic output and the experimental data, and the result was expressed by the some kind of a confidence intervals, the upper bound and lower bound. And based on that, we made decision whether the model is valid or not. That was the case in the previous class. And today, we move to the case of a computer model is not deterministic. So this is today's class. We will consider the model under uncertainty. And the validation metric is also introduced for this case. And in case of this, I think I told you already about there are two types of uncertainty. One is the aleatory. In other words, this is also known as the inherent uncertainty, physical uncertainty, irreducible uncertainty. We cannot reduce the uncertainty in this case. And the other case was the epistemic uncertainty. It comes from the lack of our knowledge on that parameter. And it also, in contrast to this one, it also can be reduced if we have further knowledge of that. So we'll show these two cases using a simple example today, and put this uncertainty into the computer model. And what we get is not just a single value, but the distribution of the output. And using this, and also from the same case, experimental data includes their uncertainty. So this is also a kind of a distribution. This is a distribution. So two distributions are gathered into the validation matrix and make decision whether they are in agreement or not. By the way, I have a remark on this here. Some examples in the previous class showed a substantial discrepancy or the bias between the model and the experimental data. And at that time, I told you that this will be addressed sometime in the later class. Will be like next week. So today, still, I don't address this issue. Instead, I just let you know this was the things like this. What is the meaning of the discrepancy? I can explain those things using the examples that I showed you in the previous class. Hope you remember this example. I'm not interested in what specific detail is this. I just showed you the results. In the end, what we got was the error or difference between the model and the experimental data. The error should be located somewhere around the 0. In that case, it is a good agreement. But what we see now here is the behavior like this. So we can see the large discrepancy or difference at the early part of the range of this distance. And in that case, we say there is a strong or substantial bias of the model from the experimental data. And there is a way that can take care of that. And I will explain that in the future. This is the same thing. The model output is the solid curve. Experimental data is this linear equation, linear straight line. So up to here, there is a good agreement, but from that moment, you see there are substantial difference. Another case of a bias. The same thing. The last example I showed in the last class. This is the model prediction, and this is the experimental data and their uncertainty bounds. You see substantial difference between the model and the experimental data. All these kinds we call the bias or discrepancy. So that was the thing in this sentence. So for today's class, I introduced 2 examples. One from myself, the other from the textbook. So this is from myself. I made this example. And the computer model here, obviously very easy and simple, just this function. And this function was taken from this paper. But there is not much issue that I'm talking today in this paper. I just borrowed the function that he addressed. And this author, I already introduced the famous paper, Kennedy and O'Hagan, with the title Bayesian Calibration. That was a famous paper. And one of the authors of that paper made also this very easy to read paper, as the title says, at this time. So I took the function that he addressed here like this. Using this function, what I consider is, at first, the deterministic case. Very easy. We would like to get the output, or y, at this point. Is 3.5. Put here and get the output, and the result is 6.45. We will move, and we already know the function, so we can plot the curve of or the function in this figure. This is x, this is y, and this is the function. And what we got here is the y value at 3.5. And now we move to the case of aleatory uncertainty. In case of aleatory uncertainty, what we consider is that the x is no longer the deterministic value. X has some kind of a probability distribution. And for just an example, I assume that x follows the normal distribution with the mean 3.5 and the standard deviation that. Because x follows this distribution, we can generate or make random samples using whatever method. Like in this case, 10,000. And we can carry out computing y at each individual value of these samples. Then we get the same number of samples of y. It's easy to capture the idea. Then using that results, we can do whatever we like.
How did you choose the 1.2 as your standard deviation?
Standard deviation just for the illustration. If you don't like, you change that value. And what we do now, in terms of this figure, is this. We have a 3.5 here, but it is the mean of that distribution. We have a normally distributed shape like this. We have a high likelihood of x around here, much less likelihood at far from here. And we make calculation at every sample points we made. And the result will be another kind of a distribution of y along this axis. And what you can expect from this figure and the curve is that at least the value of y will not be above 7, because the function itself doesn't allow that. And this is the real result based on the 10,000 number of samples of x and the 10,000 number of y, the histogram. And it doesn't exceed value 7, as I told you. And we don't know the specific shape or the type of distribution. It's a random distribution, an arbitrary distribution. And using this, we can also go to the plotting the CDF, cumulative distribution function. The definition is at a certain value, for example, at x. No, this is not x, sorry. In this case, the x-axis represents y, because this is turned into this CDF, and this represents the distribution of y. So please be careful. The x-axis represents here the y. So at a value y, if the y value is 5, and if we got the value of 0.2, that means that the probability of y less than 5 is 0.2. That is the definition of a cumulative distribution function. And this is the MATLAB source code. Yes?
Is there a specific reason you chose the input uncertainty to be a normal distribution?
No. If you don't like that, you just try y-bar, log normal, whatever.
Okay.
Yeah. Now we will move to the epistemic uncertainty. In this case, we have two cases of epistemic uncertainty. One is due to the lack of data in terms of input variable. Remember, go back to the previous slide. This assumption came from where? This assumption ideally came from the infinite number of data. And we made this value, model parameters. But in practice, it's not the case. We have only a few number of data for x. So we cannot assume that the population mean is this and the standard deviation is that. So this is the case. Input x is what we have for this information is only a few number of data with 5. And we got the sample, not the population. the mean of the sample was this. And the standard deviation, in this case, for simplicity, we just assume that we know the standard deviation of population, which is 1.2, just for simplicity. If you'd like to add this, you can do that also. So in this case, we assume that we don't know the true mean. Instead, we just have the sample mean. And we know the standard deviation. That is the case here. Then I taught you in the first part of this lecture. In that case, we will have a posterior distribution based on the Bayesian statistics, and the result was this. The result was the unknown mean, mu, will follow the normal distribution with the mean at x bar, sample mean, and its standard deviation becomes the original standard deviation divided by square root n. And n is 5 here. So in this case, unlike the previous one, we have the distributed mu. What was that in the previous case? It was a single value, 3.5. Now, it is distributed. So in this case, we have to go through the double loop process. At first, we generate samples for mu following this distribution. Then each individual sample, we go through the lh13 process that we went through previously. So that's why we call it double loop process. This is the source code. Yes?
So this one, you don't, so what is sigma squared?
Sigma square is standard variance and the square of the standard deviation.
So that's the sample standard deviation?
No, just for simplicity, I just assume that we know already the population standard deviation. But if you don't like that, you regard this as a sample standard deviation. There is another equation to take care of that. And I also taught about that. But in this case, just for the simplicity, I just introduced that this case. So what we get from this double loop process, as I told you, we can make the samples of the mean, mu x. In this case, I use the 50 samples. So we have 50 samples of mu x. And at each individual mu x, we go through the Monte Carlo, and we get the CDF. So ultimately, as a final result, what we get is the 50 number of CDFs. And we can draw it together here. So what we see is the range of CDF values from this figure. The next case under the example 1 is another kind of epistemic uncertainty. Previously, the function we saw was because you did not pay attention to the function, but you can compare what was there and what is here. The difference is here. It was just a fixed value 2. Now it is turned into a parameter u. And to be honest, the experts in this function tells now it was not 2. Frankly speaking, it was somewhere between this and this. And this is the case, lack of knowledge. And in this case, we will consider the x again as a aleatory uncertainty. So for this case, what we see now is the mixture of the aleatory and epistemic uncertainty. X is the aleatory uncertainty, as in the first example I showed you, and the U is the epistemic uncertainty with this information. In this case, we also have to go through the double loop process because of the U, the characteristics of U. We have to assume that U will be given by the uniform distribution with this information and make samples that follows that distribution. Again, I introduce 50 numbers and go through the same process I did before. In that case, I make also, again, the 50 number of CDFs, and the result is given here. Yes?
Why do you use a double loop simulation instead of one sample of epistemic uncertainty and then one sample of aleatory uncertainty?
Yes. Your question is why didn't you use apply both probability information into the function at the same time? Very difficult question that I can answer. Yeah, because the type of the uncertainty, the difference of the type of the uncertainty, we have to treat it separately. And I will show you. You made a very good question. I will show you what happens when we do like you said. It is in the result in the next slide. The second example is from the textbook. The problem is about the steady state heat transfer through a solid like this. We have a boundary condition at the left side, or in this textbook, it's called the wet side. Temperature is 300. On the right side or the east side, temperature, this value. And the bottom side or south, it is adiabatic. And the upper side, there is a convection heat transfer with this formula. There are input uncertainties. One from the conductivity. And the conductivity is assumed as the aleatory uncertainty with this distribution. Another uncertainty comes from the heat convection. The experts in this problem tells me that he thinks that H will be located somewhere between these. So this is the epistemic uncertainty. This is the aleatory uncertainty. So we go through the double loop process. 10 samples of heat convection coefficients are made in the textbook. If you don't like that, you can increase by yourself to 1,000, whatever. But in the textbook, for the illustration, 10 samples are introduced. At each of the heat convection coefficients, we solve the heat conductivity problem. But on top of that, we have the distributed conductivity. We generate samples for this. There was no indication. Yes, in that case, 1,000 samples of K were made. So 1,000 number of solutions should be made for this. And on top of that, we have 10 samples of H. So grand total will be 10,000 analysis. And what he got from this problem was this. The 10 numbers of a CDF here. And also, there is another figure at the bottom. And it is given once again in the next slide. We call this as a P box. P box represents the although in this case we generate only 10 number of CDFs, ideally we can make an infinite number of CDFs, and we can think about the outer boundary of those CDFs or envelope, and we call that as a P-box in the textbook. And P-box comes from the epistemic uncertainty. Remark is the answer to your question. When we treat this uniformly distributed H as another lh13 uncertainty together with X, one will obtain the dotted CDF here. And this should be distinguished from the one that we are considering. In terms of how to deal with these uncertainties, the textbook explains there are two ways. One is to use the Bayesian inference. Obviously, I like this method. And the other one is his method, the textbook's method. And the textbook doesn't like Bayesian. So the textbook doesn't treat the Bayesian in detail. There is rarely no Bayesian stuff in the textbook. His preference is a probability-bound analysis. And within this method, there are also two kinds of approaches. One is the nested double loop. I already introduced you in this example. And the other is the, so they called evidence theory, or in other name, the Dempster-Schaefer theory. And this method was actively studied by a group of research scientists for the last 10 years. I know that, but I didn't apply or implement myself about that because I prefer the Bayesian approach than that. Whatever the method is, the result we get is the same thing, this one, the P-box. So the range of CDF is the result we get. And the probability at some value, the probability is not a single value, but an interval valued quantity in that case. Now we move to the validation metric. First, in case of aleatory. Next, in case of epistemic. So this is the first, the aleatory uncertainty. I told you we have two outputs, one from the model, the other from the experiment. From the model, we also have the distribution. But in that case, we say it can be the continuous distribution, unlike the experiment. So theoretically, the CDF of the model can be written in this way. Very easy equation. This is the PDF. This is the CDF. On the other hand, in the experimental data, we need to introduce some kind of a distribution, and the textbook introduces it as the empirical distribution function, or EDF. I also call this as the empirical CDF, the same thing. And I would explain this equation using the examples. Let's consider we have data only one data at 1.5. The empirical CDF for this case is just this figure. Before 1.5, we have 0 probability. After 1.5, we have unit probability. The next case, when we have three data, 1.2, 5, and 3.3, based on this definition, what we get is this figure. Before 1.2, 0 probability. 1.2 and 1.5, we have a 1/3 probability. And the later interval, we have a 2/3 probability. And above that, we have a unit probability. That is the definition of an empirical CDF. By increasing the number up to the case like this, we can virtually generate experimental data using this distribution information, generate 100 data, and also apply the same thing, we get this results. As we increase more and more data, we get to the CDF that we are familiar with. So when we have only a few data, it looks like this. And we have many more data, we will get the figure like this. We have two distributions, one from the model, the other from the experiments. And how to compare the two? And what is the metric? And the textbook introduces several different ways for that. At first, the easiest, the primitive way is just take a look at the two results side by side, the figure of the distribution. And the next is a little more quantitative comparison. Compute the moments such as a mean, variance, and others means the higher moments like skewness, kurtosis. Compute this information from each of the results and compare. That is the second way. And the third way is to use the so-called Kolmogorov-Smirnov tests, which means it is to compute the maximum difference of the two CDFs. And this is the typical way of the comparison in the traditional statistics. But the textbook introduces his own way for comparison, for validation, which is the area metric. And the metric is given by this equation. But it is much easier by looking at the figures to understand the meaning of this. This is nothing but the difference, the shaded area that represents the difference between the two CDFs. One from the empirical, the other from the model. In case of one data, I told you it's just like this shape. In case of multiple data, the empirical CDF will behave like this, and the CDF from the model will behave like this, and we find the shaded area, that overlap between the two. This is the definition of the area metric, and he is suggesting this way. And when I prepare this material, I keep in mind that the students will use this metric in their homework problem, paper helicopter. So they should use this kind of a metric to validate the model. The first remark from the textbook, the area metric that he introduced is obviously better than comparing just the moments. I agree, because the figures explain the reason. Even if we have the agreement with both mean and standard deviation, we can have a different situation. One, closer agreement, the other, less closer agreement. In that case, the area metric, using the area metric is much better to identify those differences. So the emphasis is that only when the two agrees closely at every point, then we will say the two is perfectly in agreement. Next remark. The textbook claims that the area metric is better than the traditional Kolmogorov-Smirnov metric. You can compare the case in these two figures. Based on the KS metric, the definition is the maximum difference between the two CDF. So you can easily see the results is 1 because the maximum difference between the two CDF at an arbitrary point is here. So 1. This case, the maximum difference, you can easily see that the result is 0.6 because the difference is here 0.2, 0.4, and the difference between the two CDF here is 0.6. So maximum is 0.6, as you see here. Based on their metric, what we can conclude? The smaller value is better. So this is better than this, based on their metric, the Kolmogorov-Smirnov metric. But from our viewpoints, from engineering viewpoints, I cannot accept that this is better than this. This is better. I agree. And using the area metric, we can make it. So that is why he introduced his metric here. Another one is given in these two cases. The Kolmogorov-Smirnov metric, the maximum difference of CDF between this and this, we have 1, the value of 1 here. What? Also the same 1. But viewing from the engineering side, we have a different metric. This is less better than this one. This is better than this one. So we have another way to identify these difference. Error metric is that solution. Yes?
With like the area metric, you still get error even if your points lie on the function. No, right?
I'm sorry?
If your experimental observations are on top of the like.
Yeah, in case we have perfect agreement between the model and experiment, which should be possible only when we have an infinite number of data, and plot it on top of the model, then we will get a perfect agreement, a single CDF curve, and the area metric is 0.
But not for the area one, right?
But not for the area. Because the area metric is defined as the difference between the two CDFs.
Yeah, because I'm just imagining if I had points on that curve and they were like sparsely on there, I would get an area. Like.
In case we have only a few number of experimental data, and it's very good to overlap on the model CDF, we still have the area in that case. And that represents our, the level of validation between the model and the experiment. Yes?
So is there any, are there any issues with using the area metric? For example, it could be that the two different ECDFs have the same area metric, but they probably have have a different KS metric. 'Cause you
So your
add-
question is the opposite case. We have a same area metric for the two cases, but the Kolmogorov-Smirnov metric is different.
Because you add area, you subtract area. You can change it several ways so that, I mean, the area metric remains constant, but your Kolmogorov-Smirnov statistic will change. So
There's an absolute value of the
I didn't think about that.
you can have absolute value.
right, that's what I'm saying. So you can do it several ways, several ECDF.
In that case, I'd like to say we'd like to focus on the important meaning of this idea. And the third remark from the textbook was, even when the model has only a finite number of outputs, which is the case when the computational cost is expensive. And we see these cases frequently. In this case, the model CDF also follows some kind of empirical way. Even in that case, the area metric can be easily calculated. So here's some remark on the P-box using the three different cases. The first case is when we have only the epistemic uncertainty. In that case, we get the result like this, literally box. And below this value, we have a 0 probability. And between these intervals, we have a range of CDF. So from 0 to 1 probability we have. And above this value, we have definitely probability of 1. So case 1 is the result of when we have only epistemic uncertainty. Case C is, again, the opposite end, opposite case of when we have lh13 uncertainty only. And case B is in between, mixture of lh13 and epistemic uncertainty. So in this case, when at a certain value, we'd like to find out a CDF value, we don't get a single value. We have to have a range of CDF value because of the epistemic uncertainty. And the area metric under the epistemic uncertainty is the same thing. Explaining theoretically is much more difficult. Explaining using the some cases as shown in this figure is easier. So you just take a look at this and you will make it. We have results from a mixture of lh13 and epistemic uncertainty. So we get a P-box like this. We have experimental data. Just as an example, we have only one data. So the empirical CDF will look like this. And if the empirical CDF is given at this location, the area metric will be 0. If the empirical CDF is given like this, the area metric is the shaded area here. So due to my lack of skill for the explanation, the area represents the area difference between the outside of the P-box and the empirical CDF. This, you will find it, what it means. And this is the homework. And by doing this homework, you will fully understand what the uncertainty means and the validation metric means. And I wonder the due dates normally. What is the due dates when the homework is given? 1 week from today, or? Yes, so from today I will give you 1 week, and I am going to have a recitation next week. Today I don't have recitation, so in the recitation time I will explain some more about that homework. And at that time you will already have finished your homework. Yeah.
So it's due on Wednesday?
Yes. Yeah.
Can you make it possible like Friday or something? Because the school is not even open, and if we have a question, we cannot really ask questions.
Next year.
Working on homework, you know, because Friday and Monday we're off, and when we come back, it's like starting Wednesday, and we have a question then.
Yeah, there won't be any office hours either on Friday or Monday.
Okay. So due dates, yeah, I will accept it on Friday, and on Wednesday I will give you a recitation.